Hey, welcome back, my friends. Today's topic is more about electricity and gravitation comparison. And this actually is a topic that I wanted to make a video for a long time, but this is going to be very short and quick video. It's going to be roughly 10 minutes of video here. So there are so much similarity. There's so much of similarity between electric field, potential energy, force, and all that with gravitation, between gravitation and electricity. And if you do one-to-one comparison on that, you really find a lot of things will actually simplify, because in the case of gravitation, I can see things going down and up. So not up but down. I can see the things falling, but in the case of electricity, I don't see electrons repelling each other or electron proton attracting each other. So it's more like visual thingy that works in favor of gravitation. So let's do it's a very quick video here. It's going to be very quick. So I'm going to compare things between gravity and electricity. So first of all, as I've already done in my previous video, the force is given here by Coulomb's law, right? Coulomb's law is basically k times q1 q2 by d square, and this is very easy to understand, but when we go to fields, you will actually see few things that are not spoken about in most of the books, and that is the reason I thought of making a video on this, because books do not talk about gravitational field, they talk about electrical field only. So what is electrical field? Hypothetically, if I put a charge here, let's say 1 coulomb of charge here at this point. So how much is the force experienced by that charge? That is called the electric field, and it's a piece of cake. Everybody has done that. So let's say there's a charge q here at a distance of d. I want to find the electrical field. So electrical field at this point is equal to k times q divided by d square. That's electrical field. Now, what's gravitational field? Again, go back. So, electrical field is if I put 1 coulomb of charge here, the force experienced by that. By symmetry there, if I put 1 kilogram of mass here, the force experienced by that. So, isn't that basically, let's say there is a mass here, and at a distance of d from that, I want to find gravitational field. I don't know the symbol, but nobody has thought about it, I think. But the gravitational field is going to be g times the mass divided by d square. So that's the field over there. But now let's talk more about it. Chota g that we talk about. So basically this gravitational field for the earth is same as this small g. So G is the electrical, E is the electrical field. I am saying the gravitational field is chota g, because think about that. If this is Earth, let's say I will change the fonts here. So this is Earth. Now I'm saying, okay, at this point, if I put 1 kilogram of mass, how much is the force? The force experienced by that is G multiplied by the mass of the Earth divided by radius of Earth square, because we are very close to the Earth, we don't care. So isn't this the force experienced by 1 kilogram, and that is chota g. So one-to-one analogy there, electrical field is same as the gravitational field, and if you talk about the units, g is usually written in most of the books as 9.8 meters per second square, but it's not, I'm saying no, this is a field. So you can also say this is 9.8 newtons per kilogram, because 1 kilogram experiences 9.8 newtons, 2 kilogram experiences 19.6 newtons, and that's why this is the field. The next thing is potential energy. Now think about two charges separated by a distance of d. The potential energy is equal to k times q1 over q2 divided by d. That's the potential energy between two charges out there. I'll have to keep moving my picture here. I'm really sorry for small space here. But think about potential energy in case of gravitation. Isn't it exactly similar? G times mass 1, mass 2 divided by the distance between those two objects. And now the fact that this is attractive in nature, it's a negative potential energy. Even in the case of charges, if they are attractive forces, the potential energy is negative, and if one is negative, one is positive, I meant. So if they are opposite charges like negative and positive, they are attractive charges. So then with that attractive force, you will have a negative potential energy. Otherwise, it's a positive potential. So that's one-to-one analogy. Another thing like field, gravitational field, the books don't talk about. Similarly, though they do not talk about gravitational potential. So what is potential? Let's talk about potential in case of electricity. Potential of this point is the amount of work you do to bring 1 coulomb of positive charge. So let's say 1 coulomb of positive charge was sitting at infinity. How much work do I do to bring to this point? And that comes out to be some number. So that's coming out to be in joules per coulombs. That's the potential of this point. How do I calculate the potential of this point? Because of this charge q at a distance of d, the potential is going to be kq by d. That's the potential, right? 1 coulomb of charge from infinity to this point. That's the potential. Now, gravitational potential is exactly similar. Let's say 1 kilogram, not positive, but it's 1 kilogram of mass sitting at infinity. How much work do I do to bring to this point? That's going to be in kilogram, joules per kilogram. My mistake. So joules per kilogram, because kilograms is what we are interested in. 1 kilogram ke liye kitna work done? Now, why would you have to do work? Because of this mass sitting here at a distance of d, the amount of work that you do is going to be g times mass divided by d. That is the potential of this point. Now, how do these things relate with gravity chota g? Very, very easy. So let's talk about, this is the surface of the earth. I am at a height of h, at a distance of h here. The potential of this point is basically, you can calculate this, but you can also simplify this, because close to the surface of earth we keep using that chota g. So basically the potential of this point is gh, because from elementary perspective, when you do not study all this g mm by d, you say okay, mgh is amount of work that you need to do to raise that object. So for every 1 kilogram you need gh amount of work here. Now, compared to this green, this red level has higher height, more height. So this has more potential, as in you need more amount of work, more potential. You need more amount of work to be done when you raise that object. So every point on green line here is equipotential. Think about that way. Because you need same amount of work done to bring it to any of these points. And if you want to carry the charge, sorry, in this case mass, from this point to this point, you don't do any work against gravity. In the horizontal line, you don't do any work because they are at the same potential. So every point here is equipotential. Similarly, every point here is equipotential. Now compare that to a charge. When you study charges later on, so let's say there is a charge q here. If I draw a sphere, this is just a sphere, this is not a circle, this is a three-dimensional structure. So potential here is same as potential here is same as potential here from electricity perspective. Same thing when you have a mass here, you have equipotential surface around that. So if you draw a sphere here around the earth maybe, so every point on that surface of the sphere is going to be equipotential. So if I go back to my original thing here, the potential at a point is given by the expression kq by d, and you would have a very symmetric kind of thing here that is going to be g m by d. So that's all. So what I'm trying to say is I have just introduced you to these facts. Sit down and then try to analyze it. Think about it. When I raise it by a height of this much, this is the work done. So what is the work done for 1 kilogram? That is gh amount of work done, because mass is 1. So at this position, this point, this position is at the potential of gh. This is at higher potential. This is a higher potential. So as you're going further and further, you're going more and more potential there. So that's all. I mean, I know this is a tiny video, but upcoming video is going to be Gauss law. I'm really not getting time for that. I'm going to be traveling for next 1 week. I promise I'm going to bring another video maybe next weekend. Pakka promise. Okay. So until then, Never stop doing your best just because someone does not give you credit. Getting credit or not doesn't make any difference to you. Give your best and you're going to achieve your goals. Until you achieve your goals, do more and more, better and better and better. So till then, bye bye, see you.